Let's skip the fluff and just admit the painful mistake that even A-star students are making right now. You're walking into your physics exams fully confident, but you are throwing away guaranteed marks on simple speed time graph questions due to basic, entirely avoidable errors. It's a massive trap in the Cambridge IGCSE Physics 0625 paper, and today, in this explainer, we're going to fix it once and for all. Okay, let's dive right into this trap. Why exactly are grade A students dropping marks here? Listen, it's not because you don't understand the physics. You get the physics perfectly fine. The harsh reality is that you are losing critical grade boundaries because of sloppy habits. We're talking missing units, rounding your calculations way too early, and making completely unforced graph access errors. To stop the bleed, we use this four-step Cambridge answer framework to guarantee every single method mark. You start with the underlying concept, you back it up instantly with evidence and data from the graph, you apply your scientific reasoning, and then you package the whole thing in precise examiner wording. If you skip even one of these steps, you bleed marks. It is literally that simple. Now, in a moment, I'll show you the exact examiner clue that changes the acceleration answer completely. But first, you need the framework that makes that clue totally obvious. Because without this foundation, you're just going to be guessing, and we definitely do not guess when our grades are on the line. Core mechanics, speed versus velocity. Let's build that framework, starting with the absolute fundamentals. The crucial point here is remembering the difference between these two terms. Speed is just a scalar quantity. It's merely distance divided by time. It only cares about magnitude. Velocity, however, is a vector. It demands both a speed and a specific direction. Mixing these two up in your examiner wording is a one-way ticket to a lower grade band. Keep these core rules locked in your mind. The gradient, or slope, of a distance time graph, that represents speed. But if you're looking at a speed time graph, that exact same gradient suddenly gives you acceleration. And remember, the area underneath that speed time curve, that gives you the total distance traveled. Also, keep in mind that for laboratory settings, light gates and interrupt cards are the gold standard for capturing the speed data accurately. The Bloodhound LSR Challenge, applying the framework. Now let's see how this builds when we apply it to a high-stakes Cambridge-style data practical. Imagine you're asked to sketch a speed time graph for the Bloodhound LSR during a practice run. You must assume it accelerates uniformly until it reaches the measured mile, and then it uniformly decelerates so that it comes to rest exactly 12 miles later. But hold on, before you even touch a calculator, you have a massive decision to make regarding the number 1610. You have to decide whether to convert that 12-mile data into SI units. In physics, standard units are everything. You have to remember that 1 mile equals exactly 1610 meters. If you just plug the number 12 directly into a speed equation expecting meters per second, your final answer will be completely useless. So here is the real test of your graph skills. If I give you the maximum acceleration and deceleration of the vehicle, you have to work backwards. You literally reverse engineer the geometry of the motion, using the area under the graph to find the total time and minimum track distance. We all know acceleration is the change of speed divided by time, and here is the payoff for sticking with me, that examiner clue I mentioned earlier. A negative acceleration is precisely the same as a deceleration. If an exam asks for deceleration and your calculation gives you a negative number, just state the positive magnitude. But if they ask for acceleration and the object is slowing down, you must include the negative sign. That one simple clue dictates whether or not you get the final mark. Flawed versus top band answers. Spot the error. Let's put your examiner hat on and do a quick spot the error challenge, because spotting bad answers is the absolute fastest way to improve your own. Take a close look at this flawed answer. The vehicle speeds up really fast, reaches a max speed, and then slows down to 0 before the 12 miles ends. Okay, pause the explainer right here and predict exactly why this will score 0 marks on an exam. Think about our four-step framework. Where's the data? Where's the scientific reasoning? All right, here is the examiner-style correction. That flawed answer was vague, it totally lacked SI units, and it had 0 mathematical proof. Now look at the top band answer. It explicitly states uniform acceleration, it references calculating the gradient, and it shows the exact conversion of 12 miles to 19,320 meters to find the total time from the area under the graph. It grounds the conclusion in hard, undeniable data rather than vague assumptions. That is exactly how you secure top marks. Mastering practical exam data. Avoiding the traps. To consistently write those top band answers, we need to master our final practical data checks. Because honestly, even with perfect theory, a practical data slip-up will cost you dearly. This checklist is your ultimate defense. You must avoid missing units. Never round too early in your calculations. Keep those raw decimals in your calculator until the very final step. Check graph scales carefully because examiners love tricky axes. Always ensure conclusions are supported by actual data, and when asked, suggest realistic improvements for your apparatus. As part of your data analysis, you might even be asked to compare the bloodhound's intense deceleration to the standard acceleration of freefall. You need to know off the top of your head that this constant acceleration of an object falling freely under Earth's gravity is 9.81 meters per second squared. Comparing experimental data to known physical constants is a classic high-level exam strategy. And if you're adapting this massive, real-world scenario to a smaller laboratory question, you've got to remember your practical tools. Light gates and interrupt cards are your go-to apparatus for measuring speed with high accuracy in a lab setting. Why? Because they completely remove human reaction time errors from your ticker tape or trolley experiments. So, we fix the data trap. We've mastered the units, and we know our graphs inside out. But leaving your wording to chance is still a massive risk. Which brings us to the deeper code. Understanding the physics is only step one. Understanding what the examiner is actually asking you to do with that physics is step two. And that correction sequence continues in our next explainer. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations, and let's jump straight over to decode the exact command words that dictate your final grade. Because before you go, ask yourself this. You might have memorized every single physics formula in the syllabus, but if you don't know the secret language of the examiner, does your knowledge even matter? See you there.